Lecture 7.3, Day 1, Volumes by Slicing. The photo is Little Rock Central High School in Little Rock, Arkansas. It is the site of the 1957 desegregation crisis. Find the volume of the pyramid. And of course, we have a formula for the volume of a pyramid, but today we're going to use calculus. Consider a horizontal slice through the pyramid. The shape of that slice would be a square, so the volume of the slice would be s squared dh. dh is a very small change in the height. And because the slice is so thin, we can ignore the bevel on the edge. If we put 0 at the top of the pyramid and make down the positive direction, then S equals H. The volume of a slice then is H squared dH. If we integrate from 0 to 3, H squared dH, we get 1/3 H cubed from 0 to 3, or 9. This correlates with the formula, volume equals 1/3 the area of the base times the height, which would be 1/3 times 9 times 3, or also 9. This is the method of slicing. Step 1, sketch the solid and a typical cross-section. Step 2, find a formula for v of x. Notice that I used v of x instead of a of x, which is what the book uses. 3, find the limits of integration. 4, integrate v of x to find volume. This is one of my favorite slicing examples because the results are somewhat surprising. A 45-degree wedge is cut from a cylinder of radius 3 as shown. Picture a large cylindrical cheese, or perhaps a section of telephone pole, and you got a new chainsaw for your birthday. Anyway, we have a wedge. Find the volume of the wedge. You could slice this wedge shape several ways, but the simplest cross-section is a rectangle. Slice this way. Now we add our x and y coordinate system. If we let h equal the height of the slice, then the volume of the slice is v of x equals 2y times h dx. So the width of the slice is y in this direction and y in this direction, or 2y. The height we'll call h, and the thickness is a very small change in x dx. Since the wedge is conveniently cut at a 45-degree angle, h equals x. And since the base is a circle, we can use the equation of a circle to relate x and y. So y equals the square root of 9 minus x squared. Substituting in these expressions for y and h, v of x now becomes 2 times radical 9 minus x squared times x dx. Adding up all the slices, the volume is the integral from 0 to 3 of 2x times radical 9 minus x squared dx. We notice an expression and its derivative in the integral, so we'll treat this as a substitution problem. We let u equal 9 minus x squared, so du equals negative 2x dx. Finding new limits of integration, we have u of 0 equals 9 and u of 3 equals 0. So our volume now becomes negative the integral from 9 to 0 u to the 1/2 du. Taking the antiderivative, we have 2/3 u to the 3/2, and we drop the negative sign, so we reverse the limits of integration. So now it's from 0 to 9. Substituting in the 9, we get 2/3 times 27, or 18. Now what surprised me about this the first time I saw this problem was that even though we started with a cylinder, pi does not enter the calculation at all, and we get an integer for the answer. Now we'll finish with something easy, Cavalieri's theorem. Two solids with equal altitudes and identical parallel cross-sections have the same volume. Picture a stack of coins. If we push it over sideways, it doesn't change the volume. We still have identical cross-sections, so when we integrate, we'd get identical volumes.